Okay, so in the last lecture we started with the Z transform, and this is the continuation of the previous lecture. So let us continue. So we know we found out the Z transform of basic signals like del of n, comma u of n, and then we found the Z transform of alpha n times u of n, and then r to the n cos of n omega naught u of n, and then r to the n sin of n omega naught u of n, right? Now if you look at this, all are right sided sequence. Simply we can say RSS. That means it starts at n is equal to 0 and keep on goes up to infinity, I mean towards the right hand side. Now in general, therefore if g of n has a Z transform, let me call capital G of Z, then from this above examples del of n, u of n, alpha times alpha to the n u of n, you realize that this G of Z would be a rational function. Okay. For example, if you take alpha to the n u of n Z transform, then it is going to be 1 by 1 minus alpha to the Z minus 1 or Z dot by Z minus alpha, like this. So rational function means ratio of polynomials. Okay. So in the numerator I have numerator polynomial, the denominator I have denominator polynomial. So ratio of two polynomials. Okay. So rational function is a ratio of polynomials. What is a rational number? It is a ratio of integers. Rational number is ratio of integers, and rational polynomial is ratio of functions. Okay. Rational function is a ratio of polynomials. Okay. For example, pi is not a rational number. Okay, though it is 22 by 7, it is not a rational number. Okay, but 1 by 3, yes, it's a rational number. Although it cannot be truncated, I mean it is a infinite duration in number. Okay, 1 by 3 is equal to 0.3333, like that, keep on goes infinite terms. But 1 by 3 is a rational number. Okay. So what will be the form of these factors? Like G of Z. 1 minute, I missed somewhere else. One second. So I think okay, yeah, I got it now. Okay, now let us look at the ratio. So let us take out the ratio of two polynomials. So in the numerator polynomial, let me denote by p of z, and the denominator polynomial, let me denote by q of z, right? So I can write this polynomial as k times the numerator I will write in this form 1 plus p1 coefficient, some coefficient p1 times z to the minus 1 plus p suffix 2 z to the minus 2 plus and so on and so forth. Let us say I have m number of terms z to the minus capital M in the numerator, and in the denominator 1 plus q1 times z to the minus 1 q2 times z to the minus 2 plus dot 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 plus q suffix n capital N times z to the minus n. And this is the discipline that we will follow. Okay, the constant terms in both the numerator and the denominator will be 1. Look at the constant term is 1, the denominator also constant term will be 1. If it is not 1, then you can pull out from the polynomial and make it 1. Okay, and this discipline we will follow. So both the numerator and the denominator will be the constant terms in both the numerator and the denominator will be 1. So this is how I achieve it, okay, by taking out a constant. And this m and n may be different. Okay, sometimes m is greater than n, or m is equal to n, or capital M can be less than n. Okay, we will consider the most general case. If you have a polynomial of degree m in z inverse, then the fundamental theorem of algebra, if you have polynomial of degree m in z inverse, from the fundamental theorem of algebra says that it must have capital M number of roots, okay, or capital M number of factors. Okay, let us denote the numerator factors as 1 minus tau times z1, where tau is the factor, okay, roots. And here p of z is a numerator polynomial, and q of z is the denominator polynomial, right? Now what is a polynomial? As I said, polynomial is a finite series. Polynomial is a finite series. Okay, for example, if you take e to the z is not a polynomial. Okay, it is not a polynomial. Why is it not a polynomial? Because it is infinite. Okay, similarly sin theta is also not a polynomial. It is it has infinite number of terms. Okay, so g of z is a finite polynomial having only integral positive powers of the variable. For example, if you write 1 plus x squared, then this is a polynomial. But if you write 1 plus x to the minus 1 plus x to the minus 2, then it is not a polynomial. Polynomial in what? X. But this guy is a polynomial in x to the minus 1. Okay, this is a polynomial in x minus 1, but this is not a polynomial in terms of x. Therefore, in general, our g of z, although we write as p of z over q of z, it will be the ratio of polynomials in z power minus 1, z power minus 1, z power minus 2, z power minus n, z to the minus 1, like this. So it is a polynomial. This g of z is polynomial or rational function in, rational function in z to the minus 1, and this is polynomial in z to the minus 1, and this denominator also polynomial in z to the minus 1. That's it. Okay, therefore from the fundamental theorem of algebra, the numerator has m number of factors and the denominator has n number of factors. Okay, so let me write down these factors as the numerator. I have m number of factors, right? 1 minus, let's say tau times z to the minus 1, let's say tau 1, and 1 minus tau 2 times z to the minus 1 dot 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 1 minus tau suffix capital M z to the minus n. This all are products in the numerator. Similarly, in the denominator, I have 1 minus lambda 1 times z to the minus 1, 1 minus lambda 2 times z to the minus 2 dot 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 up to 1 minus lambda suffix capital N z to the minus 1. So these all are factors. It is in the product form. So in compact notation, I can write this as follows: k times product of I is equal to 1 to capital M 1 minus tau I z to the minus 1. In the denominator, I can write pi of, let's say L is equal to 1 to capital N 1 minus lambda suffix L z to the minus 1. Okay, so the numerator is a polynomial of degree capital M. So it must have capital M number of linear factors. These all are linear factors. Each factor will be this form: 1 minus tau I times z to the minus 1, because we have contrived to make the constant term equal to unity. If you look at here, this constant term is 1. So because of that, we are getting this form. Okay, so this is continued product. We can write in the form of continued product because of the constant term is 1. The denominator also we have like that. Okay, we have contrived to make the constant term equal to unity. So if you look at here, I put look at this term, contrived to 1. Okay, we made that term to 1. So because of that, in this form you are getting 1 minus tau 1 times z to the minus 1 multiplied by 1 minus tau 2 times z to the minus 2, and so on and so forth. If you don't make this constant as 1, then you don't get this format. Well, I can write it in this form. Suppose I take z to the minus 1 out from each of these factors. See, the numerator has m number of factors and the denominator has n number of factors. I would like to take out z to the minus 1 from each factor. Therefore, in the numerator I can take m number of z inverse. So z to the minus m, the denominator I can take z to the minus n. So continued product of I is equal to 1 to a capital M, then this is z minus tau I. The denominator, continued product of z minus lambda suffix L, where L is equal to 0 to capital N, 1 to capital N. Okay. So if you rearrange this, k times z to the n minus capital M pi of z minus tau I is equal to 1 to capital M, continued product of z minus lambda L, where L is equal to 1 to capital N, like this. Okay, now at these values, when I say z equal to tau I, what will happen? The function becomes 0. Therefore this tau i's are called zeros of g of z. And at these values, when z equal to lambda L, then the function blows up, right? G of z blows up. Blows up means what? G of z becomes infinity. Therefore this lambda L's are called poles. The tau i's are called zeros of g of z and lambda L's are called poles. It appears that the function has m number of zeros and n number of poles. M number of zeros and capital N number of poles. So the function g of z has capital M number of zeros and capital N number of poles. But then something is hidden here. Okay, you look at here, something is hidden. Something is hidden here. Like if n is greater than capital M, then I will have n minus m zeros at the origin. Am I correct? Yes, n minus m zeros at the origin. Okay. Similarly, if capital M is less than capital N is less than capital M, then I will have n minus m poles at the origin. In general, for any rational function, the numerator of the number of poles must be equal to the number of zeros, including the points at the origin and infinity. Therefore, your lambda L's and tau i's are poles and zeros, excluding the point at the origin. So these are zeros and poles, or poles and zeros, excluding the point. On the other hand, if n is equal to capital M, then we have no problem. Okay, that is the same number of poles and the same number of zeros, nothing at the origin, nothing at the infinity. Okay, now let us take finite and infinite sequences and let us see how the poles and the zeros differ. So to start with, let me take finite sequences. Finite sequences. If the sequence is finite, for example, we take sequence x of n is equal to 1 to 1. This is n is equal to 0. Now you take the z transform. If this is a sequence, then what is its z transform? X of z is equal to summation of x of n z to the minus n, lower limit is minus infinity, upper limit is plus infinity. I have only 3 samples. One is situated at minus 1, 0, and this is n is equal to plus 1. Therefore, summation of the summation becomes x of minus 1 z plus x of 0 times z to the 0, then x of 1 times z to the minus 1. What is x of minus 1? 1. So z plus x of 0 is 2 plus z to the minus 1. This is my z transform. Okay, z plus 2 plus z inverse. And therefore, for a finite sequence, we may have a pole at the origin, due to this z to the minus 1, and 0 at the origin, okay, due to this z. Okay. Similarly, I can say this z is a pole at infinity. Therefore, for a finite sequence, z equal to 0 is a pole and z equal to infinity is also a pole. if the sequence starts from a value of n which is negative. On the other hand, if we have a causal sequence, that is a causal finite sequence, then no term in x of z with the positive powers. If it is causal sequence, let us say 1, 2, 1, 3 like this, if you put like that, n is equal to 0. In this case, what is going to happen? Your x of z, capital X of z is going to be 1 plus 2 times z to the minus 1 plus z to the minus 2 plus 3 times z to the minus 3. Okay. Now look at all the powers are negative. Okay. No term has positive powers, and therefore in this sequence the poles will be only at the origin. Poles will be origin, and therefore the poles will be only at the origin. So for only at the origin for a causal sequences. Okay. So in this example, if you look at, one pole is at the origin and other pole is at infinity. Now let us consider a specific case. Suppose we have an RSS sequence, that means right sided sequence. Right sided sequence starting at n is equal to 0. What do you call this sequence? It is a causal sequence, right? Because it is starting at n is equal to 0. Then its z transform will contain only negative powers. As I said, if you look at here, this all are negative powers of z, and therefore the poles, all poles will be at z equal to 0. If you put z is equal to 0, then the function becomes infinity. Therefore the ROC cannot include a pole, right? Cannot include a pole. If it includes a pole, then what is going to happen? The function will not converge, right? Because at pole the function blows up, right? G of z blows up. So if it blows up means it diverges. Therefore the ROC of RSS will be mod of z is greater than 0. You should not include 0 point. In other words, as I said, r suffix l is equal to infinity and r suffix r is equal to 0. That is, the ROC will be for RSS sequence, the ROC will be total z plane excluding total z plane excluding the origin, okay. And you know, sometimes you may not write no r suffix r equal to 0 plus, okay, don't write like that. 0 and 0 plus have the same significance here, okay. We don't distinguish unless you account for the delta function. In delta function, 0 plus and 0 minus you have to distinguish, but the point at the origin have to be excluded in our case, okay. The origin have to the point at the origin has to be excluded for a causal sequence. On the other hand, if you have an anti-causal sequence, that is a left-sided sequence, LSS starting at n is equal to 0, then all poles will be at infinity. So causal sequence, I mean right-sided sequence, okay, starting at n is equal to 0, then all poles at z equal to 0. Anti-causal sequence, left-sided sequence starting at n is equal to 0, I mean the sequence starts at n is equal to 0 and keep on goes towards the minus infinity. So such a type of sequences all poles at infinity, which means that the ROC will be mod of z is less than infinity in this case, and here mod of z is greater than 0. Okay, so here total z plane except I already wrote here except or excluding the origin, except the origin or excluding the origin, and here also total z plane excluding infinity. Okay, excluding the infinite circle or the circle with the radius of infinity. Okay, so this point we need to remember. On the other hand, suppose the first example was n is equal to -1, this is 0 and this is n is equal to 1. Now the sequence is non-causal sequence, and it starts at n is equal to -1 and goes up to n is equal to 1. Okay, started at n is equal to -1, it started from the left. It is a right sided sequence RSS starting at a point to the left of n is equal to 0. Okay, it starts to the left of your point n is equal to 0, and in this example let us say this we said 1 and this is 2 and this is 1, that is what we took, right? Let me check. Yes, 1 2 1, correct. This point is magnitude is 1 and this is 2 and this is 1, and in this example both the origin and the infinity have to be excluded. Okay, mod of z has to be excluded and the infinity also has to be excluded. So the ROC for the z transform of this example is mod of z is greater than 0 and mod of z is less than infinity. Therefore, what does it mean? This says total z plane except the infinite circle and the point at the origin, total z plane except the infinite circle and the point at the origin, the point at the origin. This example can also be made can also be considered as a left sided sequence. Yes, it is a left sided sequence starting at n is equal to +1. Either you can consider as a RSS sequence or I can say LSS sequence starting at n is equal to -1 and it goes to the left hand side. So for a sequence which is neither causal nor anti-causal, both the points at infinity and origin are excluded from the origin. So the moral of this example is a sequence which is neither causal nor anti-causal. Okay, then ROC must exclude the points at infinity and the point at 0. Okay, that's it. That's all about finite sequences. Now let us move on to infinite sequence. So how this ROC is defined for an infinite sequence. You see, in the case of a finite sequence, our z transform was a polynomial in z power -1 or a polynomial in z or a combination of the two. Agreed? So we have 1 plus z to the -1 like this, or z to the -1 plus 2 plus z to the 1 plus z to the -1 like that, right? or a combination of the two. Okay, completely in z power minus 1 or completely in z or combination of the two. So for a finite sequence, if it is not causal, neither it is anti-causal, then we have a polynomial. We have sum of two polynomials. One is in z power 1 positive z powers and another one is negative powers. So our ROC was between infinity. So in this case ROC was between between this point and this point, in between this region, excluding the origin. Now let us consider the infinite sequence. So for an infinite sequence, the z transform is a rational function again. G of z is a rational function p of z divided by q of z for infinite sequence. It is no longer a sum of two polynomials. Well, you can consider this g of z as a sum of two series, but not polynomials. Series are different from polynomials. Sum of two infinite series. Okay. This is where the distinction between series and polynomial lies. A polynomial is a finite series, right? When somebody says polynomial, then it must have a finite number of terms. Is a finite series. Whereas for an infinite sequence, either causal or anti-causal or the combination of the two, the z transform is still sum of two series, both of them are infinite. See, z plus 1 plus z to the minus 1, it is a polynomial. Suppose if you have like this 1 plus z to the minus 1 plus z to the minus 2 plus dot dot dot, then it is a series. Series has infinite number of terms. So infinite series in general you can write in a finite form as a ratio of polynomials. For example, if you take g of n is equal to alpha to the n u of n, then g of z is going to be summation of alpha to the n u of n z to the minus n minus infinity to plus infinity. So this is going to be alpha times z to the minus 1 whole to the n. It is a geometric progression. Okay. So if you expand this, 1 plus alpha times z to the minus 1 alpha times z to the minus 2 plus dot dot dot. So it is infinite sum formula. So it is going to be 1 divided by 1 minus alpha times z to the minus 1. If you simplify this, z divided by z minus alpha. Now what is p of z in this case? P of z is equal to z and q of z is equal to z minus alpha. And obviously if you locate the poles in the z plane, then okay, if you locate the poles in the z plane, it's a $1 million statement. Okay. So it is bounded by the poles. So this is very important point. ROC is bounded by poles. It's a $1 million statement. The circle on which a pole is located cannot be part of ROC. So this is a z plane, this is real of z and this is imaginary of z. Okay. In the z plane I have real of z and imaginary of z, then the ROC is bounded by the poles. Suppose if I draw a circle and if this is my ROC, then my poles will be located somewhere on the circle. So the circle cannot be a part of your ROC. Okay. If you have, let's say, a circle here, let me draw a circle. Let's say my pole is sitting somewhere here. This is a location of pole. Then obviously the ROC cannot include this pole. Okay, ROC cannot include this pole. It must be either outside this circle or it can be inside this circle. Therefore, ROC is bounded by poles. Now let me take another example. U of n we already found. The z transform of u of n is 1 divided by 1 minus z to the minus 1. Now where is the pole? The pole is located at z is equal to 1, mod of z equal to z is equal to 1. What is ROC? For other considerations we found out that the ROC is mod of z greater than 1. Therefore, draw a circle with a radius of 1 and the ROC is outside of this unit circle, and this one is imaginary of z, and this is going to be real of z. From other considerations we found out that the ROC is mod of z is greater than 1. Because at z is equal to 1 the pole lies. So in the ROC I cannot include the pole. If you include the pole, then what will happen? The function blows up, it becomes infinity. In case if you take alpha to the n u of n, then its z transform is going to be 1 divided by 1 minus alpha times z to the minus 1, where alpha is the location of the pole now. So the pole is located at z is equal to alpha, then you draw a circle with that radius r, and here this mod of z is greater than mod of alpha. Therefore, the ROC is outside of the circle whose radius is alpha. Okay, so because this is the right sided sequence and this also right sided sequence. Therefore, in general, right sided or causal infinite length sequences have an ROC outside a circle. Here also the ROC is outside the circle, and here the sequence is RSS sequence or causal sequence, and here also I took RSS sequence or causal sequence. Here also the ROC is outside the circle. So the general statement is, whenever you have a right sided sequence, then the ROC will be outside of the outermost pole. Okay. So in general, a causal infinite length sequences have an ROC outside a circle. Which circle? The highest pole, the farthest pole. Farthest pole. I may have 2 poles, 3 poles, 5 poles. Okay. So the farthest poles from the origin. Okay. So therefore the ROC circle is bounded by that. Outside that is the ROC. So let me take another example. Let us say h of n is equal to 0.2 whole to the n plus minus 0.6 whole to the n. This whole thing is multiplied by u of n. Now it is a causal sequence. See, this is also multiplied by u of n and this also multiplied by u of n. That means what? This guy starts at n is equal to 0 and keep on goes up to infinity. Therefore, both of them are right sided sequence. But now I have 2 terms, one is 0.2 and the another one is 0.6. Okay. Sum of 2 sequences. One sequence is 0.2 power n times u of n and another sequence is minus 0.6 whole power n times u of n. Now you take the z transform of this, h of z is equal to 1 divided by 1 minus 0.2 z to the minus 1 plus 1 divided by 1 plus 0.6 z to the minus 1. Why did I put plus here? Because there is a minus in this location. Now the ROC of this term only, if you consider the first sequence alone, what is the ROC? Mod of z is greater than 0.2. What about the second term ROC? Mod of z is greater than 0.6. Okay. Now let us draw the picture and then we can come to the conclusion. One pole is located at 0.2 and another pole is located at minus 0.6. Okay. Now if you simplify this, you will get z times 2 times z plus 0.4 divided by z plus 0.6 times z plus 0.4. Okay, so one pole is at point 2 and another pole is at minus 0.6 and there is a 0 at the origin. Okay, there is also a 0 at minus 0.2. Am I doing, have I done any mistake? This is 0.2, I guess. I am sorry, I did a mistake. 0.2. So the poles are z is equal to minus 0.6 and z is equal to 0.2 and there is a minus symbol. It is minus, am I right? Yeah, now I am right. So one pole at minus 0.6, another pole at 0.2. What about the numerator? These are the pole locations. 0 locations are z is equal to 0 and 2z plus 0.4 is equal to 0. If we get z is equal to minus 0.4 divided by 2. Okay, so z is equal to minus 0.2. So there is a 0 here at minus 0.2, 0 and the 0 at the origin, 2 zeros and 2 poles. Then the ROC has to be outside of the outermost pole. Which is the outermost pole? This is not the outermost pole, by the way. If you draw a circle, then it will be like this. But if you draw a circle, then what will happen? If you plot this will be the ROC. Then the ROC included this 0.6. So if you include the poles at 0.6, then the function blows up. Therefore, this inner circle cannot be an ROC. Okay, therefore I cannot consider the inner circle as the ROC. Okay, therefore I need to, I'm sorry, I draw a circle with the 0.6 and now you draw the ROC outside of the outermost pole, the farthest pole from the origin. The farthest pole from the origin is this guy, minus 0.6. Therefore, for this function, for this guy, the ROC is mod of z greater than 0.6. Okay, don't write minus 0.6 because I am taking modulus. Okay, what is the radius of the circle? Radius of the circle is 0.6. Okay, don't say minus 0.6 is the radius of the circle. Therefore, the ROC of the combination is outside of 0.6. Well, if you take individually, you are right. Okay, so this is for this guy individually, the ROC is this one. If you take this guy alone individually, the ROC is this. But if you combine these two sequences together, then the ROC must be outside of the farthest pole from the origin. Therefore, it is bounded by a circle passing through the farthest pole. Okay, causal sequences have a Z transform whose ROC is bounded by a circle passing through a farthest pole. So, okay, I just take another example to see if there exist sequences which do not have the Z transform. X of n is equal to alpha to the n. This sequence, for example, unless you add a u of n or u of minus n, it does not have Z transform, because your capital X of z is going to be summation of x of n times z to the minus n, n is equal to minus infinity plus infinity. Now, this guy is going to be alpha to the n, z to the minus n. If you do not put a u of n or u of minus n, then this is my formula to calculate x of z. Now I can break this into two summations. One is n is equal to minus infinity to 1 alpha times n z to the minus n plus summation of n is equal to 0 to infinity alpha to the n z to the minus n. Then this is going to be minus 1 alpha z to the minus 1 whole to the n plus summation of alpha z to the minus 1 whole to the n is equal to 1 to infinity. Okay, let me call this is my first summation and this is my second summation. The first summation will exist for mod of z is greater than mod of alpha, and the second summation will exist if mod of z is less than mod of alpha. So you can say that mod of z is equal to alpha, so there is an overlap, but z equal to mod of z is equal to alpha passes through a pole. Okay, so it passes through a pole, therefore it may not have z transform. So whenever you have a sequences of this type, then it doesn't have z transform and it doesn't have the ROC. So in this example, this guy has no ROC and no z transform. Okay, in z transform, the ROC is an extremely important attribute. ROC is an extremely attribute, important character. And the z transform, if the ROC is not given, okay, in case if the ROC is not given, then it is not a one-to-one transform. Okay, if ROC is not given, then z transform is not a one-to-one transform. One-to-one transform. What is the ROC of dt of t? In case if you take discrete time Fourier transform, what is ROC? It is a unit circle, right? Simply it passes through the unit circle. So there is no other region in discrete time Fourier transform. But for the z transform, the convergence will occur in general for annular region. Okay, maybe like this, annular region. Okay, annular region could be bounded by as smaller radius as 0, this can go to 0 and this can go up to infinity. Okay, as larger radius as infinity. I think this is where I should stop. So let us continue in this point.